Well, it's kind of hard to imagine that this will be most likely our final lesson of the year, especially since we still have 9 weeks to go with nothing but AP prep. We may do a few explanations, but it is the last section in the book aside from the appendices. So as we look at this very last lesson, and as we think about the upcoming summer not too far off, ladies and gentlemen, I leave you with this cartoon. Thinking about the things that you will do and how probably legally you probably shouldn't tell them to anyone, but that wouldn't be you all. You all are good students. Well, about half of you at least. So let's begin. We're going to wrap up our lessons in the calculus book by looking at calculus as it applies to polar functions. And not only polar functions, but we're also going to apply calculus to a combination of polar and parametric functions. And we'll do a variety of other things. So let's begin. Some simple stuff, some review from pre-cal, just like the parametric lesson had a lot of review, so will this one. These are your conversion formulas. If you are given an x value and you want a coordinate equivalent in polar form, we'll do r cosine theta, y is r sine theta. If we're going the other way and you want the r value given the x and the y, we'll do this. And if you want the theta value given the x and the y, we do this. Now you'll see these formulas were very similar to ones we saw in parametric. In fact, almost identical. This looked like magnitude. This was how we found directional angle. This is what we used to find component form. So the two are very, very similar. All right. Your first job is to find the rectangular equivalent of each of these polar coordinates. Now again, if you want to try this, that's fine. Pause the video. I'm going to go ahead and jump right into it. So we have an r value of 4 and a theta value of pi over 2. To find the x, we'll do 4 cosine pi over 2. To find the y, 4 sine pi over 2. Use your unit circle. Cosine pi over 2 is 0. Sine pi over 2 is 1. And so 0 times 4 is 0. 1 times 4 is 4. 0, 4. All right, 16, 5 pi over 6. 16 cosine, 16 sine, each of 5 pi over 6. What is cosine of 5 pi over 6? Well, that's negative radical 3 over 2. Sine of 5 pi over 6 is just 1/2, so we multiply those out and simplify. And then last, we have negative radical 2, cosine negative pi over 4, and same for sine. What is cosine of negative pi over 4? Well, negative pi over 4 is in the fourth quadrant, and so that's going to give cosine a positive radical 2 over 2. And sine of negative pi over 4 would be negative radical 2 over 2. So when we combine those together and multiply by the radical 2's out front, you end up with the point negative 1, 1. Now let's go the other way. What if I give you rectangular coordinates and you have to find the polar coordinates? Well, again, not really a problem. We're going to take 1, 0, which is x and y, and we'll find the r value, radical x squared plus y squared, 1 squared plus 0 squared. And then we'll do theta equals the arctangent of y over x, 0 over 1. Gives us an r value of 1. All this simplifies out to be 1. And arctangent of 0 is 0. So in this one actually has the same polar point as it does xy point. Now for negative 3, 3. Again, r is radical x squared plus y squared. Theta is the arctangent of y over x. Simplify the r out, you get 3 radical 2. Simplify the theta out here. Now this one's interesting because you're asking where is tangent equal to negative 1. And on the unit circle there are two places where tangent equals negative 1. There's 3 pi over 4 and then there's 7 pi over 4. How did I know to use 3 pi over 4? 3 pi over 4 is in the second quadrant. And if I were to plot this point on just a regular rectangular coordinate plane, it also would be in the second quadrant. So I'll make it match up. And then last, we'll do radical 1 squared plus radical 3 squared for the magnitude, or the radius, I should say. And then we'll do theta is arctangent y over x there. And again, this simplifies out to be 2. This is radical 3. Again, where is tangent equal to radical 3? Well, it's going to be at pi over 3 in the first quadrant and at 4 pi over 3 in the third. Why did I pick the one in the first quadrant? Because that's where this point would be located if I were to graph it. All right. Now, graph all the points in the plane that satisfy the given polar expression. Now, these, ladies and gentlemen, are ones that you're going to sketch on your calculator or perhaps some other device, if not your calculator. Oh, sorry about that. These first two I did just on my TI Inspired calculator. When you go to polar graphing, you do get the R equals menu. So you can type in R equals 2 and graph, and you see it's a circle of 2. So if you have R equals 2, that's technically a circle radius 2. R equals negative 2 is a circle radius of negative 2, but again, negative 2 radius is still just 2. Now, the thing is that theta equals not available on your TI Inspire, so I had to use Geometry Sketchpad to do this one. But if you have theta equals pi over 6, and the arrows are in the wrong spot on this one, but what it is you go take and you draw an arrow out toward pi over 6 and draw one away from it. This line right here, if you think about the unit circle, this would represent the pi over 6. Now, these are not based completely on the unit circle. I think it goes pi over 3, pi over 6, up like that. But this is the line pi over 6, a radian measure, and this is its opposite. So theta equals that, you have a straight line. Now, let's actually get into some fun graphing. And we did some of these in pre-cal last year, but just to refresh your memory. Go ahead and pause the video, sketch this one on your calculator. Now, if you sketched it, hopefully you got something that looks like this. This is what we call a rose. Now, a rose has all these little petals like this. Roses can have as few as one petal and as many as, well, infinitely many. You can have, just keep going forever and ever and ever. How many petals do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's determined by the number in front of the theta. If the number in front of theta is even, the number of petals is twice that amount. If the number in front of theta is odd, then whatever that number is, that's how many petals you're going to have. Alright, 1 minus 2 cosine theta. Go ahead and make that sketch right now. And we end up with this. It's a very special kind of a graph. We'll talk about it and what its name is a little later on in the lesson, but you see it's got an inner loop. It loops back. Alright, 4 sine theta. Go ahead and do that one on your calculator. Pause the video. Again, this one is another rose, but you see the number in front of theta is 1, and so it has 1 petal. Converting from polar to rectangular. Now, we've done coordinates, but is it possible to take a polar equation and then make out of it a rectangular equation? Well, it's actually not too bad. We'll start out with r equals 4 sine theta. I'll square both sides, or no, I'm sorry, not square both sides, but I'll multiply both sides by r so that I'll have an r squared over here. Now, r squared is x squared plus y squared. You may wonder about this. What is this r sine theta? Well, r sine theta, remember, one of the conversion formulas is just the formula for y. R sine theta equals y. And now I can bring the 4 over to this side, and technically this is the equation for a circle, but it's not the best equation for a circle because it's not in proper form, because I need to complete the square with this y squared minus 4y part. So I'll take half of negative 4, which is negative 2, and square it. That's 4. I'll add that. And if I add 4 to this side, I need to add 4 to this side to keep the equation balanced. This now factors to be y minus 2 squared. And now this is my equation of a circle, centered at 0, 2, with a radius of 4. Alright, parametric equations of polar graphs. We're going to combine parametrics and polar graphs together now. The polar graph r equals f theta is the curve defined parametrically by this. Now, remember we had the formula x equals r cosine theta and y equals r sine theta. Well, r is f theta, so I just make that substitution. So the x equation is f theta cosine theta, and the y is f theta sine theta. So it's very simply, actually. You just take whatever the polar equation is, and to have the x component, you slap a cosine at the end. To have the y component, you slap a sine at the end. It's very simple. Switch your calculators to parametric mode and then sketch this graph right here. Now, when I do that, I get this. And I ask a very simple question. Does this look familiar? If you were to go back a couple minutes or go back a few slides, this is the exact same graph we had just a moment ago for sine 6t. Now that makes perfect sense because look here, sine 6t, sine 6t. To do the x, I just put a cosine at the end. To do the y, I just put a sine at the end. Sine 6t. It's the exact same graph. This one was in parametric mode. The other was in, of course, polar mode. Alright, find the slope of the rose curve this, where theta is pi over 6, and use it to find the equation of the tangent line. So now we're getting into some calculus. Alright, x would be this times cosine. Y parametrically would be this times sine. Now to find the slope parametrically or polar, however you want to think about it, I just do the derivative of y on top and I do the derivative of x on the bottom. So the derivative of y, what's that going to be? What's the derivative of x? Well, to do these derivatives I have to apply the product rule. So we'll take 2 sine 3 theta times the derivative of sine, which is cosine. And then we'll take sine times the derivative of 2 sine 3 theta. Well, the derivative of sine is cosine, and I have to account for this, so the derivative of 3 theta is 3. And I'll bring that 3 out front with a 2, and that's what makes this a 6. And we'll do the same kind of thing down here. It's slightly different because of the cosine at the end instead of the sine, but you see there's a lot of similarities. And we want to know what is this function's value at, it says pi over 6. So I take pi over 6 and I plug it in. Now let me go back just a second. You take pi over 6 and you plug it in for theta here and here, there, all 8 places. Plug them in, go to your unit circle, get all of your values off your unit circle and simplify these. So if you want to do that now, go ahead and pause the video, otherwise we go on. When I get my unit circle values and I plug them in, I get these numbers right here. Of course, the 0 stuff goes away. And I can simplify everything down to be negative radical 3. Now that represents the slope of the tangent line. I still need to find the tangent line, which means I still need to find an xy coordinate point. So to find the x coordinate, I take my pi over 6 and I plug it in for theta into the original x equation that we used. And when I do that, again, unit circle values, I get x equals radical 3. To get the y coordinate, I plug pi over 6 into the y equation, y equals 1. Now I can take my coordinate point, radical 3, 1. I can take my slope, negative radical 3, and I can do my point slope form. Y minus negative 1 equals negative radical 3, x minus radical 3. And distribute your negative radical 3 through, add your 1 over here, and we get this final answer for the tangent line. Alright, more calculus. Area. The area of the region between the origin and the curve r equals f theta for theta between alpha and beta is given by this. So the area is integral from alpha to beta, and we use alpha beta because theta is an angle measure. 1/2 the function squared. So we're going to find the area of this function. Find the area in the region of the plane enclosed by the cardioid, this right here. So we'll start out by making a sketch. Go ahead and sketch that on your calculator. There's what we have. Our job is to find the area inside that curve. Now, we go 0 to 2 pi. How did I come up with the 0 to 2 pi? Well, if we go back here and you go to the table, if you go to the table, you see that a theta value of 0 gives you an r value of 1, 2, 3, 4. And then as you watch the table, it goes around and it goes around and it comes in and it goes around and around again and it comes back to the beginning at 2 pi. And again, you can look at that in the table of your calculator. So 0 to 2 pi, 1/2 the function squared. Now this is not too bad. We're going to FOIL out the 1 plus cosine theta right here. I can pull my 2 out front so that I don't have to distribute it right there. Now I'm going to do a power reduction formula. If you remember power reduction formulas from pre-cal. Now, again, and you're probably sick and tired of hearing me say this, ladies and gentlemen, but you do always have that option of just right here plugging it into your calculator. So I did my power reduction, then took the 2 that was out here and I distributed it back through, so 2 and 4, and then that gets rid of that 2 right there. Now I can take the integral, and those are not difficult integrals to take. I get 3 theta plus 4 sine theta.